look at some more examples. We have this situation now, the temperature of the room is 70 degrees. Every hour, the temperature drops by 10% of the previous temperature. So notice the key here is that it's dropping by 10% of the previous temperature. But a function describes the room temperature T hours after the room was at 70 degrees. So again, my unit here for my variable is hours. So let me create again another little table. And again, T here is then definitely hours. And I'm going to call this T of T. And this temperature in degrees Fahrenheit. All right, so at 0, it says that the room temperature was 70 degrees initially. So notice again, 70 degrees initially, we're at 70 degrees Fahrenheit. Great. Well, what happens now? In this case, every hour temperature drops by 10% of the previous temperature. The previous temperature is here. So when we go 1 hour into the future, what happens? Well, we're going to start with our original temperature, 70. And we're going to subtract from it 10% of it. So subtract 70% going down by 10%. So I'll take 10% of 70. So again, we go through this process. I see that what I have here, if I factor out that 70, what do I have? 1 minus 0.1, because the 70 is common to both. So really what I have here is 70 times 1 minus 0.1, 0.9. So if I were to come over here and just do it without having to do this, I get 10% of 70 is 7. And when I subtract, what do I get? Again, 70% of 0.09 is 63. 70 minus 7 is 63. So the temperature dropped down to 63 degrees. If I were to do this again, we go through exactly the same process. 63 minus 63 times 0.1. But again, I am subtracting because it's dropping by 10% of the previous temperature. But we do exactly the same thing. 63, if I factor that out, what do I get? 1 minus 0.1. So when I come over here, I got 63 times 0.9. Excuse me. So 63% of, again, what I have here is 63%. 10% of 63 is 6.3. If I were to carry this out, again, continuing here, at 2, I'm going to get, again, 63 minus 6.3 is 56.7. And reality is, that's what I would get here too. But just as a reminder, how do we get here? Well, to get to T equals 2, I start out with 70. Then I took 9% of it, 90% of it. And then when I got here, what am I doing for the 63? I'm taking another 90% of it. So really, to get to this 56.7 degrees Fahrenheit, I'm taking 70 and multiplying twice by 0.09 squared. Okay, so let's kind of look at things. In this case, then, the B is 0.9. And because this is between 0 and 1, notice, again, we got the scenario where between 0 and 1, the growth, the decay factor, again, factor means multiply. So these are factors because I'm multiplying. The decay factor is 0.9. While R in this case, we're dropping by 10% every time. So R is negative 0.1. Because again, I'm dropping, and the R is really negative. So again, R is less than 0. So this must be the decay rate. And now if I want to write a function, that describes 250 hours. I just follow this process. So I'm going to call this again T of T. And what do I have here is my original temperature, then my, in this case, decay factor, and raised to the Tth power. And there's my formula. Let's look at another one here. The temperature in a room is 80 degrees initially. So again, at my initial degree. Every minute, the temperature drops by 2 degrees Fahrenheit. So now what I want to do is compose, make sure you see the difference between this question and this question. Every minute, the temperature drops by 2 degrees. So let's kind of work this out. So this time T is in minutes. And again, I'm going to call this T of T. And at 0, we're at 80 degrees. And it looks like the temperature is also dropping. For every minute, temperature drops by 2 degrees. In other words, 1 minute elapses. And look at the difference here. Every hour, the temperature drops by 10% of the previous. So I need to go 10% of the previous. But that's not what this is saying. Every minute, the temperature decreases by 2 degrees. In other words, 1 minute elapses. What do I do? Subtract 2 degrees, and that gives me 78. If I go to 2, what happens now? Well, the temperature continues to drop by 2 degrees. So I go 78. So I'm still using the previous value, but I'm dropping by 2. 76. 3 minutes into this 76, I drop again. 74. And you can see I can keep this going forever. But wait a minute. This is different, right? You can see the difference here. I'm still subtracting something, but here I'm subtracting a percentage of what came before. This is, I'm subtracting a fixed amount. It's always going to be 2, 2, 2. For example, here I subtracted 10% of the previous, which gave me 7 degrees. But now 10% of the previous is 6.3, and so on. But here it's just the same amount. I'm subtracting exactly the same amount, no matter what I go. So this is not exponential. This is not exponential. Matter of fact, if I had to describe it, notice here, when I had to try to generalize it, what do I have to do? Exponential was about multiplying constantly by the same thing. So this, depending on what you decide to replace t with, at the end it says, oh, to get to the next value, if you go 5 into this, I need to multiply this 5 times with the original, and I get to my new position. But this is not what this is saying. I'm subtracting the same amount every time, doesn't change. So if I were to generalize this, how does this work? Well, call this again T of T, and looks like I start with 80 originally, but I'm subtracting the same thing. So originally I subtracted 2, then I subtract 2 again, I subtract 2 again, I subtract 2 again. I keep subtracting, you know, so I keep subtracting more each time. Depending on how many times I do this. So this is T. So I subtract, so go from exactly from 80 to 76, for example. What did I do? To do that, I had to go 80 minus, and then I did it once. I did it twice. I did it a third time. So really, I got 80 minus 2 plus 2 plus 2. In other words, 2 times 3. 80 minus 6. 80 minus 6 is 74. Okay, so really, what is the formula? The formula is just this. 80 minus how many times am I subtracting? And what I'm going to keep subtracting is the 2. So I get this. Oh, what is this? This is a linear equation. So a linear equation is always adding or subtracting the same thing. Exponential is always multiplying the same thing by something. It could be dividing too, but I mean, you can think of this as division as well. So adding, subtracting, or always adding, having your viewpoint, but that's the difference here. So this is not a exponential at all. This is just linear. So there is no, the concept of the growth factor, because we could talk about it, but I guess one of the differences is that the growth factor here, if we had to calculate it, is changing, while here it's constant. Let's look at another example. The population of a small town is described by the function P of t equals 1500 0.83 years after 2020. What is the initial value in 2020? So again, this says that t years after 2020 is what this formula gives us. So at 0, we have 1500. This is our initial. And again, if you don't see that, I can just put it into this formula. At 0, what do I have? 0.03 to the 0th power is 1, and I get 1500. So the population was 1500 people, which I can see is sitting right here. That's what this is. This is my initial condition or value. In terms of applications, that's what it's known. In terms of transformation, it just says I take this basic one, this basic function, and stretched it by a factor of 1500. So again, depending if you're looking at application or just mathematically, we have different meanings for this, but not really different meanings, but different ways of interpreting it depending on how we're currently viewing it. What is it, population 24 months after 2020? So 24 months. Okay, so that's 24 months, but what's my variable t? T is happening in years. So t is in years. So if I want to look at 24 months converts to, so 24 months equals 2 years. So really, if I want to do that, what is the, I need to enter 2 into this formula and raise that to the second power. Okay, so get a calculator here and figure this out. So what I have is 100, and I'm going to multiply this times 0.083, and I'm going to raise it with my little caret key here to the second power, and I get my value. I'm just leave it with a decimal for right now. Obviously, you can't have 35th of a person, but anyway, we're not going to worry about it at the moment. But that's what it comes out to. Okay. So now I ask, what is the decay factor? Okay, clearly we're going down, right? We started with 1500, now we're 1033, so we're going down. So what is the decay factor? Well, the factor is the thing that I'm continuing to multiply with, which is this 0.03. So what this is take 1500, and how many times I'm multiplying this 0.83. So factor means to multiply. So the decay factor is the b, which in this case is 0.83, and of course it is number 0.83 is between 0 and 1. That's why it's a decay factor, right? That's why we have it. As a decay factor, what is the decay rate? Good question. So, what a decay rate is. So, we have that b is equal to this. So, let me just kind of do this 0.083. It's 1 plus r. So, to get r, I need to subtract 1 from both sides. So, go 0.83 minus 1. That gives me r. When I take calculator and subtract, what do I get? 0.17 negative. It's r. So there's my decay rate. Again, because I'm decaying, r must be greater, less than 0. Okay, so in that case it is. R in this case is negative 0.17, and that is my decay rate.